It's already, yeah, I think we can start. Welcome everyone. Today we have a talk by Radu Roiban, and he will speak about spinning and spinless particle dynamics from gravitational scattering amplitudes. Please start.
Thank you very much for the invitation. It's a pleasure to speak here, and I have to apologize again for not being able to make it to the inaugural conference of the Institute a couple of years ago. Had to do with visa issues. So today I'm going to tell you about work that happened over the last year or so in collaboration with Zvi Bern, Andres Luna, Julio Parra-Martinez, Mikhail Ruf, Chaoshen Shen, Mikhail Solon, and Mao Zheng. So we have been knowing for quite some time about how to describe gravitational interactions, but as it turns out, every time we change the point of view and change the methods, we tend to uncover new things. And each of the new methods that have been used, like field theory, string theory, wordline approach, twistors, numerical general relativity, and so on, each of them brings a different perspective and emphasizes different aspects of gravitational interactions. Now, apart from direct applications of explicit calculations, there are other reasons to carry them out, and that is to expose structures and patterns, because once we see some structures and patterns, then we can develop new tools and ask new questions, and then we can repeat the cycle. So what do I mean by structures and explicit calculations? Well, I definitely don't mean something like this. This is definitely a true Hamiltonian describing the interaction of two massive particles in the post-Newtonian expansion. But there is no real structure here. It's just a page full of numbers and momenta and other things. I also don't mean this, which is perhaps a too explicit expression for certain observables, and this slide will appear again a little bit later in the talk. What I mean is more something of this type, nice general, or at least conjecturally general relation between certain observables like this O and certain functions, like in this case, it's the function chi, diagonal phase of a scattering amplitude. It doesn't have to be anything related to scattering amplitudes, but in the case of the talk today, we're going to focus on that. But what I mean is something like this, a general relation that covers more things at once and reduces all the needed data to perhaps a single function or a handful of functions for many observables. Another kind of structure that I have in mind is a close connection between observables and scattering amplitudes in this case, or other things, or perhaps analytic structure of observables or Hamiltonians or something of that kind. So with this in mind, here is the plan for the talk. So I will begin by telling you about classical limits of quantum field theories, specifically one of them, because there are many of them. And then after that, I will tell you a little bit about how to connect classical amplitudes to observables for hyperbolic motion of massive particles. And then I will illustrate this with showing you observables for said two-particle dynamics at order g cubed and g to the fourth. This is customarily referred to these days as the post-Minkowskian expansion. Until a few years ago, it was called just plain perturbation theory, but so I'm going to switch between the two names. So after this, I will tell you a little bit about a higher spin formalism that gives expected results in the classical limit. And then I will show you arguments why this relation I was showing you on a previous slide has a chance of being true, and it has been tested to certain orders in G and the spin. So again, the goal is to describe the interaction of heavy particles while integrating out off-shell gravitons. This turns out to be easier said than done, and perhaps you rightfully might ask the question, why worry about quantum physics or quantum scattering amplitude and take the classical limit of that rather than just stay in the classical limit to begin with? And I have to say, for the better part of the last, I don't know, 30, 40 years, people have focused on just the classical, they stayed in the classical regime and there have been tremendously interesting results that led to observations by LIGO and Virgo. But the reason to step out of the classical regime into the quantum regime and then take the classical limit afterwards is that the quantum mechanical framework turns out to be more constraining. And of course, this is intuitively clear, but there's another intuitive analogy to this, which is that of integrable models. So we know that in an integrable model, the Hamiltonian or a Hamiltonian that gives the time dependence has some structure. We just don't understand it. And we can diagonalize it until we take it and embed it in, say, the transfer matrix and diagonalize all commuting Hamiltonians at once. And this is useful and it works because this bigger framework with more commuting charges is, of course, more constraining. So that's more of a philosophical reason to step into the quantum regime and then take the classical limit afterwards. Another, which is perhaps more of a technical nature, is that there is a large amount of advanced and efficient technology that has been developed for quantum calculations. And all of that can be repurposed to do calculations also in the classical limit. So I'm talking about the generalized unitarity, the double copy, which you have heard the talk about in about 2 weeks ago or so, and I will mention it again in a little bit. And then advanced integration methods for Feynman integrals. So with this motivation to step away from the classical limit, what is the classical limit that we care about? And that is the one in which all conserved charges are large. The reason is that ultimately this enterprise wants to describe actually classically heavy particles, and well, the mass is in a sense a charge, and the corresponding angular momentum is also a charge. So that's why we want large charges. So with this in mind, the classical limit in h bar equals 1 unit is described by the limit in which the de Broglie wavelength of our particles are, on the one hand, much larger than the separation between the particles, and on the other, much larger than the size of the particles. The first one implies that the orbital angular momentum is large, which also in turn implies that the momentum of the particles is much larger than the momentum transferred between the particles here and in the following denoted by Q. This limit on the size of the particle also implies that the spin or the intrinsic angular momentum of these particles has to be much larger than 1. So in short, the classical limit that we're interested in is the one in which we expand in inverse powers of orbital angular momentum, inverse powers of the spin, or in or in the momentum transfer. And the other consequence of this little argument is that if we want to describe classically spinning particles from a quantum field theory framework, we need to come up with an approach that works classically for large spins, or ideally infinitely large spins if we want to describe infinite arbitrary multiple moments induced by the spin. So also with this, and remembering that the Newtonian potential is classical, the structure of the interaction potential between two such heavy particles has this structure. There is some coefficient which ultimately is what we want to determine, which is a function of the momentum of the particle, and then something that depends on the momentum transfer, the spin, and perhaps additional scales like, say, the size of the particle, should we make these particles to have finite size. And all of these, R times Q, Q dot S, this product here, they all scale as 1 in the classical limit. This is basically, this is what we're after. We are after computing some quantity out of which we want to extract this one little tiny bit that scales in this particular way with G Newton, the transferred momentum, the spin, and the size of the particles. By the way, I didn't mention in the beginning, but please feel free to interrupt and ask any questions at any time. Right, so
sorry, could you please comment a bit? So if you try to visualize what's happening using Feynman diagrams,
It's something like you are having two incoming legs, and then there is a kind of exchange between them.
I will get to that in about 5 minutes.
Okay.
Would it be okay to?
Yeah, sure.
All right, thanks. All right, so how do we? I mean, how do we do this? There are, of course, several approaches to doing this, here I'm listing two of them. One that has been used extensively and led to the Hamiltonian that I was showing you on the second slide of the talk, and the one that I'm going to follow. So the idea again is to start with some kind of an action, integrate out gravitons, and then find some effective action from which we extract the potential. So there is the word line approach, in which pretty much the matter particles are always treated as sources. They're always on shell. There are no antiparticles, and then there is just gravitational interactions between them. There's also an Einstein-Hilbert term here that I did not write. So the gravitons, the off-shell gravitons are integrated out. One finds an effective action, and this effective action, this effective action is basically the potential. In a second quantized approach, one needs to work a little bit harder. This is a typical starting Lagrangian, some free part and some interaction part. It does include antiparticles, and because of that, they have to be separated. There are several ways of doing this. One can construct an effective field theory by matching the scattering amplitudes of this action to those of the effective field theory. And in that effective field theory, we built in the fact that there are no antiparticles. That is, if we want to scatter, say, Earth and Mars, we want to scatter Earth and Mars, not anti-Earth and anti-Mars. Another option is to use something like, at least in the presence of spin, something like Foldy-Woodhudson transformations to separate already in this in the original action the positive and negative energy modes, and basically integrate out the negative energy modes. Ultimately, what one finds is again some kind of effective action from which one needs to from which one extracts the Hamiltonian. I will show you basically on the next slide what that is, or at least the structure of that effective field theory. The one thing that one has to keep in mind is that scattering amplitudes that are used to construct this, in fact, contain terms that scale somewhat stranger than the classical scaling I was describing here. And the reason is relatively easy to understand. We are after computing a partition function. Amplitudes, I should say, amplitudes are closely related to derivatives of a partition function. But in the partition function, we have it's e to the I gamma, and gamma has a classical bit which scales like 1 over h bar, say. So if we expand this as the scattering amplitudes do, there is an e to the I, there is an I gamma which contains the classical part, but then there are things that scale like 1 over h bar square, 1 over h bar cube, and so on. There is ultimately no information in the super classical scaling, but all of this has to be removed in order to properly find the effective action. One might say that, okay, all you have to do is take the log, and that is entirely accurate, but the logarithm is not always easy to take, at least not in this framework. And matching with the effective field theory actually does this exactly for us. So before going to actually computing stuff, it's worth discussing a little bit what do we mean by off-shell gravitons. It turns out that there are interesting off-shell gravitons for potential calculations and not so interesting gravitons for potential calculations. And the way to separate them was introduced some time ago by Beneke and Smirnov, and it goes it's known by the name of the method of regions. So the idea is to separate space of off-shell loop gravitons into several regions depending on the scales that appear in the problem. And in this problem, superficially, there is only one scale, the scale of the incoming, the energy of the incoming particle. So we have, and also the scale of the momentum transfer. And they are, as we discussed, they are very separated in the classical limit. So the hard gravitons, which are off-shell, but their energy scales like the energy of the incoming particles, those are not exactly interesting because they have no information about, say, the distance between the particles that are being scattered. The ones that carry information about that have their momenta and their energy scaling like Q, and that's because the conjugate variable to Q is the impact parameter. Now, in principle, one could just integrate over these guys and find an answer, but there is more to be said. And that has to do with the fact that since we're after a potential, potentials tend to mediate instantaneous interactions. Therefore, we need something that's instantaneous. That is, we want offshore gravitons that, in fact, have very small energy. And this separates this so-called soft region into two parts. One that's known as the potential region, in which the energy of the offshore or loop graviton scales like the transferred momentum times the velocity of the particles, and the space-like part scales like just the momentum transfer. And then there is the radiation, in which both of them scale the same way. So we will be integrating out these guys, the potential modes. And because there is this separation between the energy and the momentum of the offshore gravitons, that will mediate instantaneous interactions. There is, of course, the assumption that V is small. So philosophically, what we are doing is we are assuming V is small, we resum in V, and then we analytically continue the answer to, say, V towards V equals to 1. All right, so having said all this, this is basically the structure of the matter effective field theory that we are after. There are some particles that carry only positive energy, and then there is the potential that we are after. And once we construct this effective field theory, the classical mechanics Hamiltonian whose equations of motion we might want to solve are basically pieced together from this. The potential is this coefficient here, and then this is just the standard free energy. All right, so what are the Feynman diagrams that would enter in this effective field theory? Well, we basically have only this kind of bubble graphs. And the reason is that we have only positive energy modes in here. So everything propagates only forward in time. Here in these pictures, time runs horizontally to the right. So there is a 3-level graph, there is a 1-loop graph, there's a 2-loop graph, and so on. And if we want, say, the amplitude at order g cube, then we'll pick the g cube bit in the 3-level part. Then we'll keep the g square here and g to the 1 there, or g to the 1 in the third line, and none of the rest contribute. So, right, so once the effective field theory, Feynman diagrams are easy-ish to compute. It becomes a little bit tedious, a little, sufficiently high loop order, but all the same, they can be computed. Now, what do we do on the full theory side, and how do we take the classical limit there? And that will answer the question that was asked a little bit later. So I think it's best to illustrate this by an example, and that's basically the computation of the relativistic corrections to Newton's potential. So we have this scattering amplitude, 2 particles going in, 2 particles going out, 1 graviton is being exchanged. And the scattering amplitude is basically this. There is 1 propagator, this one, oops, the 1 over q square, and then all this stuff comes from, the second factor comes from just the 2 vertices, stress tensor up, stress tensor down, contracted, and a little bit of cleanup makes this slightly prettier. Sigma is a variable that will appear over and over again. So now in this case, there are additional terms in the numerator which are dropped. The extra terms in the numerator, what they do is they will correspond to Feynman graphs that effectively look like this. Oops. Okay, I don't seem to be able to draw. That effectively look like this. Basically, the graviton is collapsed. And this, we don't want to keep these guys because they correspond to local interactions. They don't correspond to long-range interactions. So does this answer the question that was asked, how it is actually done?
Yeah, more or less. So here, like essentially momentum transfer and like what you noted P and Q.
That's right. Q goes this way. This is Q. And yeah, this is P. This is P1. Sorry, that would be P2. Yeah, this is P2. This is P1. And yeah. Right. So as I was saying, this can be done, and we have done this up to 2 loops by just matching the Feynman graphs. Well, the amplitudes computed from Feynman graphs in the EFT and the amplitudes in GR plus scalars, and constructed the Hamiltonian up to G to the 3rd power. But it does get pretty tedious, and the reason is that Feynman integrals in relativistic Feynman integrals and Feynman integrals that appear in this effective field here, they look pretty different just because the propagators look different. So the question is there a better way to do this? Is it possible to bypass some of this matching? And the answer is an emphatic yes. And to justify that, it's useful to remember that we are after a very specific piece of scattering amplitudes, namely the one in which we integrate out potential gravitons, which, because of this imbalance between their energy and their space-like momentum, they are never on shell. That implies that on the one hand, the scattering amplitudes we are after are elastic, meaning there is equal number of particles in the initial and final state, but they also have only 2 particle cuts because there is no graviton in them that can actually go off shell. So there is this is what the second statement would mean in an optical theorem kind of framework. But there is a simple solution to this, at least a simple operator solution, and that is that the S matrix is basically a phase, where of course the phase is an operator, and so is the S matrix. So the S matrix elements are then computed by expanding this and taking the matrix elements of this thing, of phi and phi square and so on. And of course here when we compute this, the second kind of S matrix element, we introduce here identity in the form of only the 2 particle phase space. So in a sense, this in fact this exponential can be thought of as a convolution over the 2 particle phase space. And this can be done in the complete theory and in the EFT and separately. So this idea can in fact be tested without doing hard calculations in GR plus matter, or it can just be done by picking your favorite effective theory with some arbitrary potential and doing this. And in fact, I believe it has been done, for example, for the Sine-Gordon model to some. So now how do we take the classical limit of this? Well, the classical limit implies that there should be an exponential form. There's this operator becomes just some function in the classical limit, and of course there are corrections which depend on h bar, and the expansion of this in Newton's constant will in fact give our scattering amplitudes. And a little bit of work implies the following, that order G scattering amplitude is just I at order G. The 2-loop scattering, the 1-loop scattering amplitude is the quote-unquote order G square part of I plus a bit that comes from this 2-particle phase space, this one, which is an integral with 2 factors of this I, because basically that's the expectation value of phi at leading order in G, and so on. And this repeats itself. The factors of Z defined here, they are just Jacobians and related to the 2-particle phase space. So basically all we have to do is to separate the superclassical parts from the classical ones is to organize the amplitude in this fashion. Now, the question is, okay, we can do this. This is just a calculation. The question is, what is this I? Does it, I tilde, does it have any physical meaning on its own, or we are just computing stuff that, that doesn't help us much? The answer is, of course, yes, it does have a meaning. And to do this, we need to remember a little bit about Hamilton-Jacobi equations and the WKB approximation. So in the classical limit, the S matrix element with fixed initial time and position and fixed final time and position is given just by the exponential of the classical action evaluated on the trajectory. And the classical action evaluated on the trajectory is just this. Now, that's all great. There is a little bit of an issue here, because the way we do calculations in quantum field theory, we definitely don't fix the initial and final time. We may fix the initial and final x in the form of the impact parameter, but definitely not the time. Good thing, though, is that time and energy are conjugate to each other in a Legendre transform kind of way. So to transform this kind of matrix element to one in which we fix the position and the momentum, all we have to do is, again, a Legendre transform with respect to the energy, just as in I don't know, thermodynamics or so. And using the fact that the Hamiltonian or the energy is conserved, in fact, the Hamiltonian contribution completely cancels in this Legendre transform, and we end up with IR being just integral P dx, which is otherwise known as the radial action. And the differential of the radial action with respect to various variables that are interesting, like the angular momentum and the energy, has meaning. The differential with respect to the angular momentum at fixed energy is the scattering angle, and the differential with respect to the energy at fixed angular momentum happens to be the time delay. So we are in good shape. If we can construct our amplitude, put it in this form, and read off I1, I2, I3, I4, and so on, then all we have to do to construct an observable would be differentiate with respect to J. One reason this is great is that at every step of this enterprise, we are dealing only with gauge invariant quantities. This radial action is gauge invariant, the amplitude is gauge invariant, and so we are not liable to introduce gauge ambiguities. All right, so now that we know what we want to compute, let's see how to compute them. So I'm not going to spend too much time on this, because describing how to compute scattering amplitudes at group level is a longer story. But there are basically, I will just say a few words about generalized unitarity and its philosophy more specifically. And the idea is that the amplitude, the integrands of amplitudes are rational functions. And these rational functions have very definite poles at very definite positions, and they also have very definite residues of those poles. The poles are given by some graph structure, like the one shown here, and the corresponding residues, otherwise known as generalized cuts, are given by products of three amplitudes. So here I'm focusing on a pole corresponding to these four propagators going on shell. And when these guys are on shell, all these blobs are three-level scattering amplitudes, which can be computed by whatever means one has at one's disposal, either Feynman graphs or recursion relations or whatnot. So once all the poles and the pole configurations and all the residues are listed, it's a fairly straightforward construction to reassemble the integrand from this data. And effectively, this is really just a fancy way of reorganizing Feynman graphs in a way that makes cancellations having to do with gauge invariance manifest. And that's because each of these three factors that appear in these residues, they are gauge invariant. Therefore, one can already use gauge invariance to simplify these factors. So this is a fairly general construction. It applies to gauge theories. It applies to gravity. In our case, we are interested in gravitational scattering amplitudes. And we don't compute them directly, but rather we compute them by connecting them to gauge theory scattering amplitudes, either via the KLT relations or via the double copy construction. So here I'm listing the KLT relations. The double copy construction, I figured I should not review it because you had a talk from Ricardo Monteiro about it a couple of weeks ago, if I saw correctly. There is, however, one interesting technical detail that's worth mentioning. So in here, one is supposed to sum over all physical intermediate states, that is, specifically two polarizations for gravitons. Now, the projector onto physical states for a vector or for a graviton depends on a fixed and arbitrary null vector, here denoted by R. So having these physical state projectors in these state sums is, well, makes things quite complicated, even though in the big scheme of things that at the end of the day, all these R's will cancel out. It turns out that there is an algorithmic way to enforce the following. To enforce the standard word identities that related to diffeomorphism in this case, but in a way that does not make use of the transversality of the physical state of that does not participate in this word identity. So here I'm contracting with the momentum of the graviton 3, and this happens to be 0, that is identically 0, without using the fact that epsilon 4 dotted into P4 is 0. If one manages to put the 3 amplitudes entering in this construction in a form that has this property, then immediately this unphysical part of the projector cancels out because this P gets contracted with the corresponding momentum, with the corresponding graviton in the 3 amplitude factors. So the physical state sum basically collapses to just using trivial eta mu for the physical state sum. So now that we know that to construct amplitudes we need to list cuts and or residues in this, as I call them, and propagators, we need to make sure that we make our life simple and don't use cuts that give us diagrams or integrals that we know that won't contribute to our in the classical limit. So here are some kinds of diagrams that we don't want to keep. For example, this one here, it has a contact interaction between matter particles. Because of this, it cannot mediate, it cannot describe a long-range interaction. Therefore, we don't want to keep these guys. This one has a graviton loop. And intuitively, this thing cannot contribute classically because, well, there's an antiparticle floating around in here, at least for starters. And one can, of course, check that it does not have the correct scaling to contribute in the classical limit. And also, there are more interesting graphs like this, which start appearing at 2 loops and so, in which the scaling might appear correct, but it surely cannot contribute to a potential because, for example, this graviton up here, if it is in the potential region, therefore it mediates only instantaneous interaction. It means that the starting point and the end point are at the same time. Therefore, there is no time for these 2 gravitons to be exchanged. Therefore, this somehow should not contribute in the potential region. And indeed, if one computes it in the potential region, one finds that it is 0. So we want to list the cuts that weed out all these graphs and graphs and higher loop graphs that have similar features. So that's what we will do. And then we'll get a long expression, many integrals. So we need to evaluate the integrals in this potential region. And to do this, we are going to use a parametrization of momenta that was introduced long ago by Sudakov. And it has, never mind the technical details, it has the essential feature that it will take pretty much any integral at any loop order. It will expand it in the soft region first. And at the time it gets to the soft region, all integrals are reduced to finite sums of integrals that depend on a single scale. This kind of parametrization is, well, speeds up calculations enormously. One-scale integrals can be computed in a matter of minutes. Three-scale integrals, well, the same three-scale integral is basically computed in a matter of days or weeks. So carrying out this expansion is an essential step in the calculation. And of course, once we have this list of integrals, we can construct differential equations for them. And these differential equations hold regardless of the region of momenta, of loop momenta in which these integrals are evaluated. And then initial conditions are just computed in the potential region, and that gives us pretty much everything that we want or need. So this said, here is what we get. This is the radial action at order G that basically I sketched a couple of slides ago. And was originally computed by Westphal sometime in mid-80s. The one-loop radial action has been computed by Damour sometime in mid-90s, and it looks like this. The radial action at two loops, we computed it, well, we actually computed the two-loop Hamiltonian, or rather order G-cube Hamiltonian, with Bern, Chung, Solon, Shen, and Zeng a couple of years ago, and it was first organized in the form of a radial action by Kalin and Porto. So here, these are, what I'm showing here are just the cuts that contribute to here at two loops, sorry, here at one loop, the one loop radial action, or the order G square radial action and order G cube radial action. There's an interesting dependence on nu, which is this symmetric mass ratio. And if you notice, it is linear in, up to some overall factor. The dependence on momenta is, and nu is linear in nu. It was pointed out maybe about a year ago or so, excuse me, that this dependence connects the Post-Minkowskian expansion, or the G expansion, with the so-called self-force expansion, which is an expansion in it's an expansion in the ratio M1 over M2, where and M1 and they are assumed to be the ratio is assumed to be very small. So with this in mind, the three order G and order G square, they both happen to be fixed by the so-called zero self-force, which basically corresponds to a probe particle moving in a Schwarzschild background. The order G cube requires the one self-force term, which determines these two guys. And indeed, this was checked to be correct. Now, recently, we also computed the order G to the fourth, which is slightly more complicated, but not much more complicated. It still fits on a slide. There are 8 cuts to be considered. Again, they're chosen to weed out everything that doesn't contribute in the classical limit. And well, we noticed that here, the most complicated function is a logarithm. Here we proceed to dialogues and some elliptic functions. So basically, we increase the transcendentality of the answer by a factor of by one unit. We also notice that just as at order G cube, dependence on nu is linear, and indeed, as argued by Damour and Bini, Damour, and Geralico, this is consistent with what the self-force would say. At 4 loops, there would be an order G square, an order nu square term, and the self-force expansion at that order is not yet known. It is known to some extent, at least in as a series in velocity and mass at or numerically at one self-force that is to linear order in nu. All right, so now that we have amplitudes, or rather radial action, we can construct observables. And like I said, it's a simple matter of just Fourier transforming and taking a derivative with respect to J. And this would give us the scattering angle, also the time delay, should we want it. And needless to say, we compared all of this with the various PN data that's available through order G to the fourth, and everything checks out. But here we have order G to the fourth and arbitrary order in velocity, unlike the PN expansion. Now, with open orbit observables in hand, one can proceed to certain closed orbit observables, which again are computed in principle by ignoring any gravitational radiation emitted during the motion. And there is a relation pointed out by Kalin and Porto that connects the periastron advance with the scattering angle and the orbital period, or rather orbital half period, with a time delay. Now, these are great, but to actually ascertain whether there is a connection and usefulness for LIGO, it's useful to have Hamiltonians, which is in fact how we first constructed the order G cube interaction. So this was constructed, the prospects for LIGO of the order G cube were studied to some extent by Antonelli, Bonanno, Steinhoff, Van de Mint, and Vines back in 2019. And the conclusion is that the results are promising. So here you see various effective approaches and various resummations of the Newton's constant, for an expansion in Newton's constant. And the teal line here is the result for numerical GR, in which the radiation has been turned off. And the corresponding curve for binding energy versus orbital frequency based on our order G cube Hamiltonian is relatively close to it. So their conclusion was that it's worth proceeding to higher orders in the post-Minkowskian expansion, which is why we computed the order G to the fourth. However, figuring out the prospects for LIGO of order G to the fourth computed in the potential region is less straightforward because of the structure of the result. It has a number of pathologies, so to speak. It is infrared divergent, and consequently, it depends on the renormalization scale. This is no real surprise because we butchered the integration domain from the whole soft region to just the potential region, and inclusion of the radiation modes would in fact cancel the 1 over epsilon, remove the renormalization scale, and replace it with some physical scale, which depends on the process. For a scattering process, the only kinds of physical scale has to do with the impact parameter, and basically that would replace the corresponding log mu with just log of the velocity, or rather the square root of the velocity. For a closed orbit observable, it has to be something, it will replace it with something related to the orbital frequency. So to include these guys, the radiation modes, we need to both compute integrals in this bigger region that includes radiation, but there are also additional diagrams that contribute, which we have not constructed yet, but so I cannot tell you exactly what they are, but at least their structure corresponds to things known as tail terms in another effective field theory, the effective field theory in which the binary, or the two-body, is considered as a single particle and is viewed from far away, that is from the region in which these radiation gravitons, which are only a little bit off shell, can propagate and then go back and exchange further further of these radiation gravitons with the binary. All right, so this concludes what I meant to say about spinless dynamics. The thing that I want to emphasize, though, is that the structure that I was alluding to in the beginning has to do, in this case, with the analytic structure of this radial action that's written here, and the kind of functions which are visible here, and the fact that there are basically only 13 or 14 of them that that determine all orders in the radial action to all orders in velocity. So any questions about that?
Yeah, I'm sorry. You have elliptic functions at 3 loops here. It's because of the 3 loop sunset master integrals, or you have some other masters with elliptic?
That's right. Yeah, so okay. It's well, there are a number of master integrals. Some of them are, depending on how you organize them, some of them are entirely dilogarithmic. Some of them are a mixture of dilogarithmic and elliptic pieces. But yeah, it's just there is we found no way to remove these. There are no identities that we are aware of that would remove these elliptic functions, and one could see this also at the level of the differential equations for the master integrals. But yeah, it has to do with the quote unquote the choice of master integrals.
Okay.
All right. So in the remaining 12 minutes or so, let me rush through the second half of my talk, which has basically about as many slides as this one, which has to do with similar gravitational interactions of spinning objects. So as before, the goal is to use a field theory approach. And for that, we need to come up with something that is not pathological and works at infinitely large spin. So we're going to construct something like this based on the general structure of the stress tensor for higher spin theory, for higher spin interaction that was written long ago by Kriplovich and Pomeransky. And also based on the 3-point interaction of a Kerr black hole with one graviton, that is, Kerr black hole goes in, graviton goes out, Kerr black hole goes out. That was constructed by Vines maybe 3 years ago or so using GR methods. And also using, taking quite a lot of inspiration from a world line action that was constructed in this form by Levy and Steinhoff based on earlier work. Which takes this, which looks like this. E and B are the electric and magnetic components of the Riemann tensor. S is the spin vector, and D are some covariant derivatives, and C are free constant coefficients, which for the Kerr black hole are meant to be 1. And last but not least, there is another conjectured 3-point higher spin graviton amplitude, which written in terms of massive spinor helicity formally looks like this. This is the product of the spinors corresponding to the matter momenta to the power equal to the spin, which in the infinite spin limit becomes just an exponential function of q dot s. Q is again is the momentum of the graviton, and M3 scalar is just the scalar scattering amplitude, the corresponding scalar 3-point amplitude. All right, so higher spin field theories have a very long history, starting with the work of Firth and Pauli. However, to date, we don't know of one that has finitely many fields. And even if we go to infinitely many fields, the options are relatively limited. However, what we want is not something that works at the quantum level, if only because our matter fields are the only ones that have infinite spin. We are still interested only in gravitons appearing in the loop. Of course, there are the higher spin fields also appearing in the loop because you know, there's a matter line in a loop, but there is no closed loop of the matter field or of the higher spin field. Well, this this will allow us to sort of butcher the whatever we might want to write in a way that will suit our purpose. Now, the problem is that there are no-go arguments that say that once you have a higher spin field and you write something, you know, a 3-point interaction involving 2 of them and gravity, then causality will force that the coefficient of that interaction to be 0. And the argument is again based strangely enough, on scattering amplitudes. One computes first the iconal phase or the radial action, which at least at tree level, they are literally the same. And because the radial action is related to the time delay, one can construct the time delay. And since we want time delays to be positive, because well, these are massive particles, and causality requires a time delay to be positive, then it basically implies that if we demand this for every possible polarization tensor for the higher spin field and for every value of B, of the impact parameter, then this implies that the coefficients of the non-minimal couplings would vanish. So this formula holds in D strictly larger than 4. In D equals 4, there is a logarithm of B, which is a little bit harder to interpret, but it turns out to dominate over these because it's a logarithm, and at least at small b, it dominates. Anyway, so the way we are going to proceed is to find a way around. That is, we are going to construct the classical limit such that there is only one polarization tensor that dominates in that limit. And since we're after long-range interaction, we're not going to be interested in small b. We're going to be interested in some b and in some impact parameter larger than some minimal value, which is, as long as that one is not particularly small, everything is
Radu,
fine.
excuse me, can I ask something? To understand the beginning. So in the first part, you just took scalar plus gravity and computed loops with graviton in a certain region.
Yeah.
But now you're taking higher spins, which have many different types of interactions, and I guess you're going to ignore some of them. But why?
I'm going to ignore all of them except the ones with gravity.
No, but even with graviton, there are many different interactions. And
yeah, well, so I will actually include infinitely many of them. So just to, here's what I'm going to include.
And how are you going to match it with the reality, where you have the spinning body scattering of another one?
Well, sadly, I spent too much time on that, but I would mean, if I'd be happy to continue the discussion afterwards. Yes, we're going to match more or less everything. So these coefficients here, they turn out to be identical with these ones, and then they can be matched against, at least at tree level, they can be matched against, say, scattering of two Kerr black holes. And at least for that, for tree level, all of these interactions can be checked. At one loop, it's a little bit harder to check against anything because there are no results that go to all orders in spin. We checked one spin on each side, and then recently there were checks with two spins on one side and nothing on the other. And all this again matches quote unquote reality computed by purely GR means or just computed using this action.
Okay, many thanks.
Does that answer your question?
Yeah, more or less, but I will continue later.
Yeah, I have to add to actually make, for the answer to make more sense, I need to tell you a little bit more on exactly how these fields are connected to, what's the classical limit of these guys, how we are taking the classical limit. All right, so since we are already on this slide, how do we take the class? Okay, so again, we are going to force to make sure that there's a single polarization that dominates in the classical limit. So this is the action that we're going to take. So the way we are going to take the classical limit involves, well, it's a little bit funny, let's put it that way. So on the one hand, we know that higher spin fields have, they have totally symmetric polarization tensors, but they are also traceless and transverse. And implementing these two, the last two constraints in a Lagrangian is typically done with auxiliary fields. There are many of them. And for infinitely large spins, there are infinitely many of these auxiliary fields, and they all couple with gravity, and they cause a fair amount of headache. However, we need to remember what we really are after. We want to have some kind of parametrization of the spin, of the classical spin vector. And in principle, if we could prevent ourselves from using relations between Lorentz generators, for example, in a spin-a-half calculation, then we could just as well use spin-a-half. Right? All we want to make sure of is that when we have something like gamma mu nu times gamma rho sigma, gamma would be the Lorentz generator in spin-a-half representation, we don't actually do the multiplication and reduce this to the metric tensor. So basically, we are going to interpret this action in this sense. We're not going to project this phi s onto a definite spin, but we're going to keep all of the spin s minus 1 all the way to spin 0, and use this just as a, if you wish, as a placeholder that will prevent us from using relations between Lorentz generators. And since these guys will never appear in a closed loop, the number of states in them will not matter, and that will be the end of that. So here are our fields. They are going to be unconstrained, symmetric, symmetric tensors, so without the tracelessness and the transversality constraints. We're going to write them in two-component notation just because then symmetry implies tracelessness. And then everything is written as a boost acting on a polarization vector, or on a tensor product of polarization spinners, so to speak. So now, what do we pick for? What do we pick for these guys? Well, there is a very well-known state that localizes the spin in some direction while minimizing its standard deviation, and that is a coherent state. So we are going to write this size as spin-a-half coherent states and use them to construct the spin vector. And this one state, the spin coherent state, will be the one polarization tensor that will dominate in this classical limit. So with this in hand, we can play games with boosts and so on. There are all sorts of cute identities that one can derive. Like the product of two polarization tensors can be written at least to leading order in the momentum of the graviton, like so. Expectation values of Lorentz generators can be written in terms of the spin tensor and so on. So this construction actually realizes the item 1 that I was describing as we want in the classical limit. To circumvent the causality constraints, and we're just not going to take the impact parameter too small. And as it turns out, similar conclusions that in this classical limit, in the large S limit, this amplitude of Arkani, Hamed and company does not have any causality violation issues was also discussed by Guevara in some talk he gave at AAI some time ago. All right, so getting back to Zenia's question, starting from this action, one can construct the 3-point amplitude first, one graviton and an arbitrary and two of these guys. And this is what one gets. And if one compares it with Wien's stress tensor for a Kerr black hole interacting with a graviton, these C's are all fixed to be 1. So that's how contact with reality, at least at this stage, is done. Going on to one loop, one can of course compute that. It's not possible to use the one for so one loop. Like I said, it's a little bit harder, and we don't have an all ordering spin result. We did just one spin on each side, so terms that contain spin orbit like s1.l, s2.l, and also terms containing s1.s2. And this is the corresponding amplitude. It's constructed basically exactly the same as before, so I'm not going to go into any more details. And this was extended recently to include 2 spins on each side. What we did first, one spin on one side is not sensitive to this, to the non-minimal couplings, because everything comes from the minimal couplings here. However, this this recent extension is sensitive to the spin square non-minimal coupling. And needless to say, everything matches with the Worldline formalism, which was essentially appeared simultaneously with this with the Luna-Kosmopoulos calculation. So the conclusion is that this formalism does capture the conservative classical physics, and at least to the extent that we checked, does not exhibit any obvious pathologies. So with this in hand, we can proceed to construct observables based on this amplitude. Now, I am already 3 minutes past 11. Am I allowed to take a few more minutes, or do I have to wrap it up?
Well, we didn't have much questions, but I think you have can have like 10 minutes at least. Should be fine.
Okay, thank you. I will try to compress everything. All right. So how do we proceed from amplitudes to observables? Well, it's basically the same as before. There are a few grains of salt to be added here, which is that in the presence of spin, some of the analytic continuation procedures are perhaps a little bit less well understood, at least by me. So there's an old saying that when you're in doubt, you should go back to what you know. And in this case, the Hamiltonian is definitely something that we know it gives the right answer. So in this case, we did construct a Hamiltonian, which does look like a pretty clumsy device. And I have to acknowledge that at some point, odds are 100% that we will circumvent the use of a Hamiltonian. But at least for now, that's good enough for us. And this is how the Hamiltonian looks like, at least the one that we constructed with Bern, Luna, Shen, and Zeng a while ago. It has only terms with S1, S2, because that was the amplitude we computed. The other terms, which involve S square, would all have exactly the same structure. The corresponding operators are up here, and their coefficients were constructed, like I said, recently, basically 2 weeks ago or so. And with this Hamiltonian, we can construct pretty much anything. We have more observables now than we had for spinless particles. We have 2 scattering angles because the motion is no longer in a plane. And we also have, of course, the 2 related spin rotations, or spin kicks, as they are sometimes called. So this is the slide I was showing you on the 3rd slide. They basically represent these observables. And in this form, there is definitely no structure to be seen. So let's search for structure in the remaining 5 minutes. And the observation is, at least to leading order in G, the observation is relatively simple. The change in pretty much any observable is given by the integral of the Poisson bracket of that observable with the Hamiltonian. Now, at order G, the potential in that Hamiltonian is just the Fourier transform of the amplitude as we constructed it. So now we have to evaluate this on the leading order trajectory, which is a straight line. And this gives us ultimately the Poisson bracket of that observable, which we assume does not have explicit time dependence. And the transverse Fourier transform of the amplitude, which is the definition of the iconal phase up to some coefficients at this order. So here is our structure. Something like this should hold at least to order G. And it does. For the change in momentum that gives the 2 scattering angles, the corresponding operator is just the transverse derivative. And for the spin, it's the spin itself. So here are those formulae. So now, can we proceed beyond this order? Well, the answer is yes. Otherwise, I wouldn't be asking the question. And there are some pieces of inspiration that we can use. First is that chi1 acts, the 1-loop iconal phase, the 3-level iconal phase acts as a sort of Hamiltonian. So one might expect that there should be an interpretation, a similar interpretation for chi2 and higher. For spinless scattering, there is a relation between the iconal phase and the impulse or the change in momentum. So one might expect the same to hold also at higher orders in G and in the presence of spin. However, one has to keep in mind that the spin is ultimately a non-abelian object because it's ultimately a matrix which has a non-zero Poisson bracket with itself. So we should expect non-linearities. So poking around, it turns out that at order G, something like this holds. The order G square change in an observable is, as one might have expected, the one loop iconal phase commuted with the observable just as a normal Hamiltonian would say. But then there are nonlinear corrections which all depend on the spin. So in here, this DSL is in a sense a half Poisson bracket involving the spin and the orbital angular momentum. It's not exactly a Poisson bracket because there the variables are conjugates, but it's this thing. So here is the structure we are looking for. All that page of tiny font that's unreadable, in fact, fits in this particular formula with exactly the same operators as at 3 level. O is just the transverse derivative for the momentum and the spin itself for the change in spin. So with this in hand, there is, of course, an all-order conjecture that one can come up with, which fits here. And to summarize for this, which is the structure that I was alluding to on early in the talk. So we have a general proof at leading order in Newton's constant, and we have explicit checks at order G square and S1, S2, and S1 square and S2 square. And based on that, one might expect that either this or something like this, a relation between chi and observables should exist to all orders. The beauty of this is that it can be checked directly in the EFT, but I will not spend more time than making that statement. Of course, we did, in checking these, one does not ultimately need the specific values for these coefficients here. One can just keep them arbitrary, and this formula will still hold. So with this, and with apologies for going over time, let me summarize. So I hope I managed to convince you that amplitudes offer a powerful way to look at gravitational interactions, at least classical gravitational interactions with and without spin. And as evidence for that, I showed you that it pushed the state of the art for spinless calculations up to currently order G to the 4th in the potential region. And in principle, there is no real obstacle except computing power to pushing it to higher orders. And also the same ideas were tested at order G square for spin-dependent Hamiltonians. And of course, there is agreement between what these methods give and available calculations which overlap, available calculations in the post-Newtonian expansion. Amplitudes also provide an inspiration to finding hidden structure and hidden simplicity, and that would be the close relation between amplitudes and radial action, amplitudes in the classical limit and the radial action. The analytic dependence of observables on velocity, this conjecture, which of course was constructed based on the idea that the iconal phase or the radial action should contain most, if not all, of the physical information. And there's more structure that I didn't tell you about, which involves objects of finite size. There are lots of things to worry about in the in short term and in longer term, like computing higher orders, both with without spin and with spin, inclusion of radiation effects, which will give us the means to connect the order G to the 4th calculations with potentially LIGO observations. Further tests and proofs of this spinning iconal conjecture, and so on. Let me not read the slides, but let me thank you for your attention, and close with mentioning that we should expect renewed progress in this field in the not too distant future. Thank you.
Thank you very much. Are there any questions?
Yeah, can I ask something about the relation to LIGO? Because what LIGO detects is the final last chirp in this signal where black holes collide, and in any case, it's about bound states rather than scattering problem. So how much of information you can actually get from scattering that would be useful for collapse of two bodies?
Okay, so the idea is so there are, you can get a lot of information depending on how you choose to look at it. So the way, the reason in this talk, I did not emphasize the Hamiltonian all that much because as we recently learned, it's a lot easier to just compute the radial action. But once you have a scattering angle, you can always reconstruct the Hamiltonian that gives that scattering angle. And with the Hamiltonian in hand, you can go back and change the boundary conditions to negative energy and use exactly the same Hamiltonian to study closed orbits. So that's about the actual motion. So here, what's on the screen now is a cartoon of that. This is the oscillations have to do with the orbital motion, and the change in the frequency has to do with the loss of energy. So the idea is that the loss of energy happens on a different scale than the scale of the motion. That is, it's much slower. So it can be added. It can be added later, so to speak, or at least in some kind of an adiabatic, way. So one can, of course, construct get information about the energy loss. There are several ways. For just open orbit observables, there's this complementary method which I did not describe in any detail due to Kassauer, maybe, and O'Connell, which does not naturally provide a way to, well, you can butcher it such that you separate potential from radiation, but it does not, it holds generically. So one can construct also the radiated momentum using basically scattering amplitudes techniques. It's not exactly scattering amplitudes because it's more something known as an event shape. It's like a cross-section which you dress the final state with some operator that you want to measure. This is, in QCD, this have been discussed forever, basically. But there is yet another way, which would amount to essentially computing, extending this EFT that I was mentioning early on and basically never talked about it again, this one. So it's possible to extend this EFT to include radiation modes. That is, additional terms that contain the graviton. So they would be, the first contribution here would come from a 5-point amplitude to this one. So the wiggly line is an outgoing graviton, and then the straight lines are matter. So this would produce a term that looks like, I don't know, A dagger, B dagger, H with some coefficient, which depends on P and momenta, specifically the momentum of the graviton. So this can be interpreted as a source, as this part can be interpreted as the stress tensor of the binary, which gives off gravitational radiation due to its motion. So one can solve Einstein's equations and the equations of motion for the matter fields together, starting from here. And in this way, one can get the waveform, which is actually what LIGO measures. So, and again, this function here, C, can be constructed from scattering amplitudes and then subsequently used with negative energy initial condition for a bound state problem.
Many thanks.
May
Oh, hi, Alex.
Yeah, hi, Radu. Well, first, maybe let me comment on the last question. I think most of what Radu was saying was rather a long answer to say how amplitude methods can be useful, but the precise stuff that Radu was talking about was about the conservative region, where indeed it's just the Hamiltonian. The Hamiltonian classically governs the same Hamiltonian classically governs the bound orbits and unbound orbits, and that's it. It's just the same thing, and that's what people use at LIGO. That's what they need. And Radu has produced new Hamiltonians for them, and that's great.
It's not like they're actually using them, but
yeah, well, that's what they that's what they should use, right? At least that's what they say they use, and then depending on their pipeline, I mean, Zvi's point was originally that their pipeline is using Hamiltonians.
Mm-hmm.
It's more like they're more used to use PN Hamiltonians than PM Hamiltonians, that is preventing them from using all these results right away.
Well,
right.
I mean, okay.
Yeah, but my impression was that really the Hamiltonians is what they like, they use, and
yes. That is
where you get this Hamiltonian from.
That is correct.
So, well, yeah. As for my question, I wanted to ask you about this nice structure, right, with the exponential, and you mentioned that at tree level at order G, you have a proof for that, and yeah, I mean, in my, I expect that to be. Is that just the statement that at tree level we know exactly how it works, like from, for example, from what I had with Alfredo and Justin, well, there's Guevara-Chervine stuff, plus the Kosover, maybe O'Connell formula.
No, I would say that this is, well...
Or do you have like a separate argument for that in a paper that I have missed?
This has not been published as far as I'm aware of, though it had appeared in talks by Chao Shen and by me at in various places. Basically, the argument is what's on the screen right now. Actually, not right now, but right here. I mean, there aren't 100 different ways to do things at tree level, so it's very likely that this can be interpreted as a rehash of your work with Alfredo and Justin. Though when we came up with it, I don't think we thought of it as a reverse engineering. But
well, yeah, in our paper we were actually relying in the tree level paper we were relying on the Kosovo maybe O'Connell formalism, and so, and you are trying to go around it. So
yeah. No, there is no,
but it's not published. Then that's what you're saying.
No, basically. This has never appeared in print.
Right.
Anyway. There is nothing more than these basically in this slide.
Okay. Yeah.
And I mean, it holds pretty much as generally as you want. In the tree level, Eikonol phase is a Hamiltonian, and pick your observable and commute it with it, and that gives you the change.
Mm-hmm.
That's all there is there.
Okay. Okay, yeah, and maybe another little question. You were referring to the one loop results that you matched to our stuff.
Yes.
So that
I forget exactly where, but yeah.
Well, just that slide that where you are. I'm not sure. Yeah, this one.
Yeah, okay.
You see here that it says it agrees.
Yeah, but this is specifically for tree level. This slide is about still just the icon of the square is the order.
But the aligned spin result is not tree level.
Yeah, so the aligned. Okay, did I say anything about aligned spin?
Well, that
yeah,
thing
okay,
was
so that's right. That reference is for more. The aligned spin actually does, as far as I remember, it agrees beyond 3 level as well. It agrees at order G square. But again, you guys have lots of spins. We have only S1, S2.
yeah. We went to. I mean, formally we have an all spin result, but we just don't trust it beyond S4.
Yeah. Andres and Dimitrios, they, as far as I know, they compared with your result also at order S square.
Yeah.
And that seems to be fine as well.
Okay, good. Because it's not written in the paper,
Oh.
so I was worried a little bit.
Maybe I shouldn't put words in their mouth then. That was my
well, it's not
impression.
explicitly written. They are citing us. They have more obvious things to check against because they have their paper and Raphael's paper are simultaneous. So it's a more stringent check to say that they agree among themselves, because that's way beyond a line spin. Anyway, yeah, thanks a lot.
Radu, I have a question. So what changes if you say have effective Lagrangian which involves high derivatives of curvature? So you just need to add some extra vertices and nothing else?
So this Lagrangian that we are using has higher derivatives of curvature. They're right here. They're just correlated with the number of spins.
No, but I meant Einstein Lagrangian.
Oh, Einstein Lagrangian.
Yes.
Virtually nothing. Just I mean, the formula should still hold. It's just that well, actually,
you may have you may have.
I mean, there are purely gravitational vertices that will start decorating these the various diagrams. But so at one loop, there won't unless the propagators are corrected, nothing will change.
Yeah.
The first place where it will be corrected is starting at 2 loops, where the actually let me take that back. If the 3 graviton vertex is corrected, then this will affect this graph here.
Yes. So, but there is a correction, like R cube term corrects 3-point function.
Right. So just R cube has okay. So this so in this sense, there is it has to come with a very special coefficient, or rather very special. It has to come with an additional mass, with an additional scale, which is large, right? So this Lagrangian here is quote unquote balanced in the sense that when we take the spin to be large, each spin is accompanied by a momentum of the graviton, which is small, which is of the order of the transfer momentum. So there's a q dot s, which is everywhere, which is of order 1. If one just adds R cube, then that will produce 6 graviton momenta, which, when thrown into a graph that likes to have, say, 2 graviton momenta, like the standard 3 graviton vertex, it will become subleading in the classical limit, unless excuse me, unless the coefficient of that R cube term is taken to be large. Right? What?
Okay, yeah, that should be, in fact, it should be very small. Well,
yeah. So what?
For other reasons, yeah. Okay, thank you.
But actually, isn't that interaction precisely the one ruled out by that argument in Camanio, Bayedov, Moldacena? Who else was there? Well, that paper that you in the beginning on the causality grounds, that when you put that interaction with a big coefficient, then it just breaks causality. So you're not allowed to.
Well, okay, let me try this on you then. All right, that R cube term, start with string theory and construct its effective action. You will get an R to some power, maybe even R cube in the bosonic string set, maybe an R cube. We believe string theory to be consistent. Then somehow something somewhere will have to fix that the problem that Maldacena, Camanio and company assigned to the R cube. Right? Maybe the infinitely massive string states will somehow fix it. The additional higher dimension operators will fix that somehow. I can't answer the question how that happens because I don't know. I wish I knew. But
well, I don't think it's ruled out as a term per se. I think it's ruled out with a coefficient that goes sufficiently large to be relevant for the classical limit.
Oh, that.
In that sense. And whatever string theory would introduce would probably be relevant.
Oh, okay. It will be
the classical
small.
limit,
Okay.
as you were saying.
Mm-hmm.
So I'm rather agreeing with you than trying to say something more.
Still, one is in principle free to ask the question, okay, imagine that you put it in. Let's see what happens. One doesn't really need to assume the coefficient to be large or small, just keep it free.
Yeah, but it still has a mass dimension, so it must be assigned a scale, and if you start with string theory, it will be some string scale, right?
Yeah, I'm not arguing that it should be compared with anything, just as a philosophical question.
I'm actually reading a paper by the Imperial group, the Durham Tolley, so they're Arkadi's colleagues that criticize Maldacena's paper, and I'm trying to understand more exactly the criticism.
I missed that paper.
From last year. It seems like they don't believe that argument that much. And
well, there is, I mean, since we're deviating in that direction, there is, of course, in dimensions larger than 4, I don't see anything particularly strange with the argument. But in dimension 4, there is wiggle room because of the logarithm. The logarithm is large.
Yeah, there's the IR scale that is not explicitly written in that paper, and that also is very confusing to me. How that IR scale, which is supposed to be bigger than everything else, may be negated by a big scale in that R cubed term. So it seems like it's quite a trivial constraint. This causality constraint in D equals 4 seems quite trivial to start with.
Yeah, so my philosophy on that was to think of it more of an analytic continuation from D larger than 4, but that might not be the right way to think about it.
Yeah, I think there was some other viewpoint that maybe you should be looking at not the complete time delay, but the difference between 2 time delays at different impact parameters, and that also has to be somehow positive, and that should also be a causality constraint. And then you remove that infrared scale altogether. But I cannot say I understand and agree. To agree with that, I would have to understand it better. So it's confusing.
Okay, it seems that we don't have any further questions. So thank you very much for a nice talk, and thank you everyone for coming. Yeah, thanks a lot. And see you next time.
See you next time, maybe even in Moscow.
Well, thanks, Radu. Yeah, thanks.
Thanks.